Hello, everybody, and welcome to our class on clustering, where we're going to try and find the similarity between genomic files. So for example, our ChiPseq files right now, we have a list of positions of where those peaks are, and we can see the similarity across our samples. If does one DNA binding protein bind to the same regions as the other one, and which ones are similar and which ones are different. That's what clustering will really do for us in the end. And you can think of it kind of as a family tree of these are the most similar to, and then going down from there into, more and more similar groups. And we'll go over all that using our custom ChiPseq data set. And so let's get started. We're in classes 2023, and we are going to go into clustering and O3 clustering RMD. And this is the code I will be using in my RStudio. Or if you're following on the web at long-noncodingrna.io/teaching, then we have now moved into Metaplots. We're going to consider clustering Metaplots because it's saying, on average, how similar is a given sample to another one. Okay, so we will go here, and where we're going to start with this is we have a matrix we made in peak features 01, where we took all the promoters are the columns and the rows are the DNA binding proteins. And what we asked for each one was there a peak that overlapped that promoter. And so we get a 1 if it did overlap the promoter and a 0 if it didn't. So we have 7, in my case, I have 7 DNA binding proteins. So I have 7 rows and 36,000 some columns, each one being a unique promoter. And so for a given DNA binding protein, we can say, how similar are you across all these promoters, all 36,000 of them? How similar are you to my 36,000 length string? And that's called correlation, and we'll do that. So we're going to need to correlate the samples, and then we can plot how far away those similarities are using clustering or dendrograms. Okay, so we're going to start with this peak occurrence matrix we made in 01 peak features, and we called it long non-coding mRNA promoter peak occurrence matrix, where it's just lincRNA and mRNA promoters and whether there's an overlap in a given consensus file. Okay. So, and again, we're using the consensus peaks for, this takes a minute to load in. I had it loaded in, but we used the peaks that were the same in all replicates to do the overlaps of the promoters to create this promoter peak occurrence matrix. And then once that loads, we are going to change it into a matrix by using this as.matrix function here, and just call it peak, or write over it and call it promoter peak occurrence matrix. And what we're going to do from there is applicable to any data sets you have in genomics, RNA-seq, ATAC-seq, anything fits in using the distance metrics between overlaps and then clustering those distances. Okay, so let's take a look at what we got, making a matrix here. And then what I'm doing here is just indexing into the first 2 rows and columns 19 through 24. I don't want to print out all of these columns here. And so if we take a look at it, what we can see is, as we thought, the columns are the promoter gene IDs of the promoters and whether there's an overlap. And I picked this because this is where we finally see one, that H3K27 overlaps this promoter, but EP300 does not. So that's just a quick peek of what we got out of promoter peak occurrence matrix. And we have a custom function in the my class functions to run that. Okay, so we can take a look at what information we have with row names. So we now know the row names are the names of our DBPs, and the column names are all the different gene promoters. And so let's just take the first 2 rows. So the first 2 DNA binding proteins. In my data set, I think it's EP300. I can't remember the second one. And then keep all the columns. That's why it's empty. And this is the important part to remember, is right now we're saying is how similar across my peak file, across all the promoters, how similar does our overlap pattern look? And so we need a statistic to do that distance similarity. And usually you use Euclidean or other methods that can handle wide fluctuations in data from, say, like values of 1 to 10,000 and everything in between. That's a much better method of finding the distance between values of that range. Whereas we just have ones and zeros. So the method we actually want to use is binary here. So you can compare what you get with Euclidean, but if we look at the method, well, let's just look at it. What we see is we get a correlation value of 91. And so that's just odd. And that's because Euclidean doesn't handle small switches of just two values to find the correlation between two samples. So here we're going to do it in binary, same idea, taking our occurrence matrix of all the promoters as columns, DBPs as rows, taking the first two rows and comparing them using binary. And that makes more sense. So we can see the overlap between EP300 and H3K27 trimethyl is quite high with a correlation of 0.9 or 99%. So similarity. So that's pretty good. And we can do this across the entire promoter peak occurrence matrix using this distance function. And so now what we're going to do is just make a smaller data frame or values of the correlations between all pairwise across my 7 proteins. Okay, so let's do that. So now we're going to do this across all 7. And so we're going to see this matrix get bigger. Okay, sorry, smaller, because yeah, that's right. We're just measuring the correlation values instead of the entire values of the data set. So if we take a look at this, it's quite handy that we have all the pairwise comparisons here with EP300 and H3K27, what we just looked at, that correlation value. And we can see HDAC, R-core1, and H3K4 are the only ones that have fairly different values here. And so my guess is these are going to cluster together as more similar than these ones over here. Okay, but I've run this before. I think I remember it right. Okay, so now we have these distances, and now we need to cluster them. And that's sort of complicated to look by eye, but I say this one's more similar to this one, et cetera. So what HClust will do is we needed the distances. We got that with distance. We got these values. And now we're going to organize them by similarity. And so that's going to happen with HClust over the object we just made. We're looking at it here, and method complete. You can look at more options here, but to save time, there's other ways of doing it, but this will work for our purposes using method complete. Okay, so let's make an object called binary hierarchical clustering, and we'll do HClust across this and organize the samples values that we're looking at here. Okay, now we can just use base R, which we did with HClust, and base R with plot, and we can already see what's happening here, that indeed these two are odd, as we thought, HDAC and R-core1 and H3K4 tri. So they're over here, and what we're looking at is the two that are most similar are here, because this is the first branch in the tree, and there's no distance really between them. And if we look here at K36 versus K27, we see that they're nearly identical, with being being 1 actually. So that's why there's no distance in the bar. And we can then see with EP300, it's still quite similar, but it does have a different distance compared to 1. That's here. And then these ones are more similar to each other and very different from these ones. So we can already start to see differences in our samples and say, oh, interesting, K4 trimethylation is tracking with HDAC2, and K36 and K27 trimethylation are tracking. Just as a first thing, we would have to do some things to look at that. And we can actually get the values from that plotted this if you want. There's so many programs, and we're going to go through things that will make heat maps and do the same thing. I just wanted to show you this in sort of a based R sort of fashion. And we can see that really we do kind of have two groups with different similarities between the heights, and this is just the distance of the branches. And you can order them if you want by going into bin here, has these different values and the order of them. And so just information to know that there's positions in here that can be sorted different ways and other things. And here, if you want to save it, you can run this PDF function, rerun the plot, and then save it there. Okay, so now we're going to make a dendrogram using a program called Dendrogram that we loaded in up here. This might have been the first time we used it, so you'll have to install Dendro to move forward. And so what it needs is the same thing. It needs a distance matrix, which we just looked at here, and rotate, size. These are all parameters that are in Dendro that you can look at. And we are just going to you can see usually they have different ways of presenting it, whether it's left to right or up, down. And so each one different sort of dendrogram program is going to have this, and just basically plot it once and then switch it to true if you want it one direction or the other. So these are just kind of like aesthetic parameters, and this is the data frame or the data that it's going to plot from. This is just to actually do that, to flip it, we can do coordinate flip and then scale Y, X continuous, and we're putting the top position on the top, value on the top, and breaks so that each element has a label by the order of their similarity position. And this is just a lot of specifying this figure to look nice. The key thing, all you really need is this here, where we can see that if we run just this, what we get is something just fine. So you don't need to learn all of this figure making yet, but if you want to come back and sort of tweak it and make it look to your custom interest, that's one way to do it. So this is a pretty nice way of seeing the data. We can kind of see two groups, one over here and one over here in our data, and we're starting to learn something. And then we can see that this coordinate flip just turned it sideways. And you can sort of walk through a ggplot and see what each different thing did. So what did the scale of continuous do? You can just run and test it as it's sort of building on itself there. So, okay, and then if we run the whole thing here, we get this other nice thing. But again, that first line we ran was probably good enough. And you can bring these into Illustrator or other vector programs and manipulate them from there. Okay, so let's now cluster our samples. We just saw the similarities based on all promoters. What if one of our DNA binding proteins prefers lincRNA or mRNA promoters? Maybe they would cluster differently if we separated those parts of the promoter peak occurrence matrix, which is made up of the combination of both of them currently. So to do that, we're going to first load in our long non-coding RNA mRNA promoters object we made in O1 peak features. I told you these would be handy. So now instead of running all that code, we can just load it in. And then what we're going to do next after that loads in is index into it and subset it by gene type lincRNA. We did that also in peak 1 features, went over this sort of indexing, but basically the square brackets means subset all the promoters to just those in gene type lincRNA, and that we'll call that lincRNA promoters. Okay, so we'll now index now that that's run. And do the same thing for mRNA promoters. Gene type is protein coding is the name for mRNA in this annotation. Okay, so now what we have here is something to index into our promoter peak occurrence matrix with. So we just made a set of objects that tells us where the lincRNA and mRNA promoter gene IDs are. And that's the name of the columns in our promoter peak occurrence matrix, because the columns are the promoters. So we can now go in and just say the ones with the gene ID or the ensemble ID of lincRNA promoters object that we just subsetted here, only take those columns and keep all the rows. So my 7 DNA binding proteins will be there, but it's only going to take the columns of lincRNAs, and then we'll make a matrix of that, calculate the distances and cluster them. And then we'll do the same for mRNA and then compare the two and see how they're different. So we're just reiterating the same kind of code, and also just seeing how indexing is really handy and creating these objects that you use over and over again. Okay, so we now have our promoter peak occurrence separated down just to lincRNAs, and now I can do this HClust. I'm going to do this in combination. We did it in steps above, but so distance, we're going to run distance on this matrix, and then we're going to cluster it, and then we can just plot it. Okay, and we're going to use binary because of the 1s and 0s in the data it's made of. Okay, so this might take a second. There isn't so bad. Now we have a distance of the different, we have the same thing we just saw above, but now for just lincRNA promoters. Let's just look at it here. Okay, so what we can see is what we did is we clustered them based on the similarity of the samples in bin here, long non-coding RNA. We can see actually that there's similar, that these 3 HDAC K4 tri went that way, and these 2 were highly similar again. So that similarity we saw, there was no difference in lincRNA promoters in that similarity that we saw in the first one. And so now we can save that if you want with ggSave, since we used a GG Dendro object maker. And now we're going to do the exact same thing for mRNAs. I won't go over it as in detail, but we're just subsetting for the columns that match the mRNA IDs, finding the distance now across all of those, which is about half the number of promoters, and then making the dendrogram. And we see the same thing, these 3 here, they might be in a slightly different order. I don't know, going slow. No, they're in the same order here. And again, we see the similarity of these 2. So we can now have a result that long non-coding RNA and mRNA promoters don't really change the properties of the similarity of their binding. So it means that they don't prefer a lincRNA or mRNA promoter for their binding. Okay, so let's look at what we can do now is say, okay, I want to know those promoters. So we have our promoter peak occurrence, and now we're going back to the one that has all the promoters in the columns, not the ones we just subsetted above to make these plots. And we can say, what are the call sums that are greater than 5? So that means that at least 5 of my 7 proteins bound to that promoter. So we're looking at it from a little bit different perspective here, that the number of DBPs in the columns where they're greater than 5 means that there was at least 5 different DBPs that overlapped there, okay, at that promoter. Okay, so we can see how many that is. Here it's only 13. And so these promoters bind 5, at least 5 of my different DBPs. So we can see EP300, 1, 2, 3, 4, 5, 6. So this must be 6 and 6, and some must have been 5 as well. So that's just a different way to index into the columns and have them make more than 5. because the rows are my DNA binding proteins. So it's summing over those 7. The max it could be is 7, and we could try and do that as well. But you can just think of it summing these columns, and the answer to these ones would be 6, which is greater than 5. Okay, and there's only 13 of them, so might as well just move on. It's not that interesting that all of these proteins don't bind to the same promoter that often. Okay, so now we can make a heat map. This is quite easy, and it'll do the clustering for us. Again, we're sort of stepping through this, just getting to know what the distance is and things like that. You'll need it again in HeatMap or pretty HeatMap here, which we loaded in above. And it's a function that we loaded in as a package. And so we need to know its parameters, look it up in the help section. And then, and you can actually Google these and get the same thing in a better format. And we're using our promoter peak occurrence that has all of the promoters, and we're gonna make a heat map on that. And we're gonna cluster the rows and the columns. So we're gonna say what promoters look similar and what DNA binding proteins, and organize that by which DNA binding proteins look similar. Really the main parameter is the data, the matrix that we have. And we're not going to show the column names because we don't need to see the name of every of the 36,000 promoters. And you could also say clustering distance columns false if you just didn't want to order them, or if you wanted to order them by the bin here or bin hierarchical clustering object we made above, you could do it that way as well. Okay, so let's run that. It's going to take a second because it has to do all the clustering. And if you want to save an object with pHeatMap or really anything else, you can do this PDF function where you set up a PDF, then you run the code and do dev off, and you'll find it show up in your files instead of up in the window here. It can be buggy, so it's good to always check your file that it's made. Since this takes a while, I'm not going to do it here, but we'll wait for the final heat map. Has a lot of values, even though it's not very complex with only 7 DNA binding proteins. We're looking at the similarity across 36,000 promoters. So it's a very wide data set. And then after that, this will be it. So we can see like a 2-dimensional version of this and see what promoters were driving this similarity. And then we're going to do a bonus thing. We're done with the clustering after this figure pops up. And then if you want to stick around, we're going to do a little bonus thing where we take peak occurrence matrix and learn pivot wider a little bit, and make it so that you can put in the promoter of your choice and get back the DNA binding proteins at that promoter. So you would have a great resource and save it as a data frame of any promoter you ended up wanting to know in HepG2 at least, what binds to it. You would know that. And when we move to the bigger data set, we'll have 480 DNA binding proteins. So you would have a lot of information if you were studying one gene about who's bound to the promoter, at least in this cell type using this data. So it's handy enough, and we have that object loaded, that it's worth going through for a few more minutes after this. But okay, so now we got our heat map back, and you can see here, not the most interesting heat map, but we can see the clustering up here of the different promoters, and then the clustering over here of the different DNA binding proteins, where we see HDAC K4 over here, and K36 and K27 over here. And what we can see that's driving that seemingly is there's very few peaks in this file here, overlapping promoters. And so maybe there's like a divide by 0, but this is why it's good to look at the data this way, as we can see there's not much going on for H3K36. And we can see that these promoters here tend to bind to these genes here. There is some overlap over here, And this is binary, so we only have a 1 and a 0, so we only get blue and red. There's no real scale here. We're going to make a bunch more heat maps with more ChiPseq data and RNA-seq data that will be more interesting. But this just gives you information about how many values are actually driving this and what the other similarity is in the second dimension. Okay, so with that, that is the end of clustering, and we're going to move on real quick to make a very handy data frame where you can pick a promoter and find out who's bound to it. All right, so the first thing we do is just simply need and we're going to need this a lot. You can see how we can just index into a bigger object and grab out long non-coding RNAs or mRNAs or whatever microRNAs, whatever annotation you're interested in. And so it's good to have just an annotation set of what are the genes names and what are the ensemble IDs. And let's just do that really quick, where we're going to merge back. This is just an exercise in tidyverse that we're going to take the link RNA promoters G ranges that we have and turn it into a data frame, merge it with, and then mRNA promoters as a data frame, and then only take the gene ID and gene name. So we'll just have a handy list of identifiers here. Okay, so let's bind the rows. So we're going to merge link RNA promoters and mRNA promoters, both of them as a data frame together, and select just these two columns with dplyr select, which we'll use often, that we just want these two columns so we can use this to grab those two. And take a look at DBPs on promoters, DBPs on promoters here. And we see all we have here is just the ensemble ID, which is in our peak occurrence matrix, how the columns are named. So this is a way we can now subset by your favorite gene, for instance, is what we're going to do now. Okay, so now that's just a handy list of the names of our promoters or genes. And all the genes and their promoters. And so now what we're going to do is take our promoter peak occurrence matrix, turn it into a data frame, and put the row names to a column. So right now the row names, if we look at row names, promoter peak occurrence matrix here, that it's our DBP names. So that means they're kind of in the meta column of the data frame, the data frame at this point, and we're going to move that name into being a column itself, a value in the data frame is what we do first here. And then we're going to get to pivot longer, and this is a great example. It's highly useful. It's complicated, so if this seems weird, it takes a minute to get used to it, but we're going to use it a bit, and it's just a handy tool to know the purpose of it to use for other goals in the future. And so if we look at what we get here in promoter DBPs, we have here, now we have, this might take a second to load because we have all 36,000 promoters in there. But what we're going to see is that it's a very long data set right now. It's 36,000 columns long and 7 observations. And so what we can do is pivot longer here. And what the nomenclature for this is, it wants to know what columns to take and make rows, move them into being rows. So the names too is from the gene ID. And so we're going to make a new, for every promoter, we're going to make a new row. So we're going to make 36,000 new rows for each DNA binding protein. Is going to have a DNA binding protein with the value of 1 or 0 for every promoter. So it's going to become super long. It's going to become 7 by 36,000 long, whereas right now it's 36,000 long by 7 rows. Okay, let's see if that has loaded for us. Okay, so yeah, so we can see this really long, really wide, I should say, data frame right now with a 1 or a 0 whether something overlaps or not. And as we saw somewhere around 19, there starts to become overlaps. And so now we're going to pivot longer. So we're going to look at this as it is very wide. We're going to pivot longer. We don't want column 1 because it's the name of the DNA binding protein. It's an actual value now in a column called DBP. So we're going to go 2 through the rest of the columns. So all the columns that represent the promoters, and we're going to take those gene IDs, make them in a row long, and then put the 1s and 0s in for that DNA binding protein, and then do that for the next DNA binding protein and the next one. And so then what we can do is filter out only to promoters where that a DNA binding protein exists. And so let's take a look at it. So let's do the pivot longer here. So now we're looking at the same, we're going to take this and just do this pivot longer here. And now if we look at promoter DBPs, it's going to load faster because it's long. And so we can see now there's a column for DBP, gene ID is what we pivoted longer on. And then we retained the values in occurrence in case there were more columns to specify this one. And so we can see that EP300 is going to have 36,000 entries, 1 for each promoter, and whether there's a 1 or a 0. So now we can filter out all the zeros and reduce this a lot, because if no DNA binding, if EP300 is not represented here, then we don't need it, because we wouldn't want to keep that. And then we do the same for all of them down the line. Okay, so we're going to filter the occurrence by 1, and we're going to see this thing shrink a lot, I'm assuming. And then we are going to take out, so let's just do that and keep doing this stepwise. Okay, now if we look at promoter DBPs, we see that the occurrence is only 1, no matter how we sort it, and the DBPs are different, and there's all 7 in there. It's 7. Now it's reduced down to only 42,000, so that's a lot lower of promoters that had any binding event for any DNA binding protein. It's essentially what we did. Okay, so we've now done the filtering, and now we're just going to take out that occurrence column because it doesn't do anything for us anymore. It's only 1s. So now we have only promoters that have binding events of my DNA binding proteins. Okay, so now we've done that, and now we're just going to left join this to get the gene name back. So we're going to try and join it back with this, which should have the same gene IDs, and get back the gene name here. Okay, so let's run that whole thing now. We've gone through it step by step. Okay, so it joined by gene ID, which was the same in both those data frames. And let's write this out. This is handy, and we might want to put it back in O1 peak features. This is probably where it fits as a repository of things we're going to index from, like link RNA promoters, mRNA promoters, etc. So now if you saved it and read it in, what's awesome is now we can take this promoter DBPs that is the same object we just made. I'll read it in. Shouldn't take that long. Yeah, okay, good. And now my favorite gene is fire. So I'm going to make an object called the fire promoter and take promoter DBPs, pipe it into just a simple filter of gene name fire. And now I'm only going to get the fire promoter, and then I'll get all the DBPs that are bound to it. So let's take a look at that. And so now I have this fire promoter object, and don't know why I didn't view. Oh, okay. So I can see, okay, there's 1 of my 7 DNA binding proteins binds to this promoter. So now imagine we have 480. It's kind of cool. It's like knowing who's there, who's at the party of the promoter, and what is your favorite gene and what's going on. So it's kind of nice to see now from a one promoter's perspective, who's bound there. And in my case, I'm seeing that fire has H3K4, and you can go through and now just filter for your favorite genes, promoter. We can look at gap DHs here, more things bound to it. We see EP300 there. This is a busy promoter. And so we can now go ahead and expand this to the 480. And I find it super useful when I find a new gene, I'm interested in it, I can go look and see who's there at the promoter. All right, that is it for today's class. And now we're going to move on to making metaplots of how or where our DNA binding proteins are bound on promoters themselves. All right, with that, thank you very much and be well.